Hi, my name is Hao, and today I'm going to talk about my implementation on the paper, ADA-INT, Learning Adaptive Intervals for 3D Lookup Tables on Real-Time Image Enhancement. The motivation behind my re-implementation is primarily three reasons. The first is the efficiency in image enhancement. The paper is motivated by the need for efficient and real-time image enhancement techniques, which is particularly important as the volume and use of digital images continue to grow across various domains. And when I was researching for the current methods, I found there's a limitation of the techniques that people are using. And in the end, the ADA-INT that is introduced by this paper seemed to provide improved quality of image enhancement. As we can see on the right hand side, the 3D LUT plus ADA-INT method delivers much more vivid image enhancement, and it's almost clear and it's almost close to the ground truth already. The problem definition here is the first is the suboptimal uniform sampling method that people are using. Previous works on the image adaptive 3D LUTs only used uniform sampling for output color values, which may not sufficiently model the local nonlinearities of the color transform, and therefore can limit the expressiveness and effectiveness of the enhancement. And then modeling color transforms, and it's hard to achieve a balance between effectiveness and efficiency. So this is a description of my implementation. I primarily changed the model.py file within the GitHub repository offered by the authors, and I rewrite some major class definition such as the LUT generator, AdaInt, and many other basic blocks. And I made a modification to the train step function as well, which is a training loop that updates the model's weights based on the data batch provided every time. So here's the example code of my optimization to the LUT generator class. As we can see in the code, it generates a basic LUT first here on line 126, and then it's going to process the final LUT based on fed input in forward function, which is done on line 144. And I use the function checkpoint here because it reduces memory usage during training by not storing intermediate activations for every layer. And this step can be crucial when working with deep networks or when limited by GPU memory. And so I was thinking if someone is trying to run the code on the relatively poor computer, which has a smaller amount of GPU memory, they can trade computational speed for it. And then I also use functions such as view and permute to ensure that the tensor is in the correct shape in the regularization function. And here is the implementation of train step function. So as we can see, it's composed of three major components here. The first is the forward propagation, which performs a forward pass with the current batch of data. And the loss computation is used to compute the loss by parsing the output from the forward pass, which includes any losses returned by the model. It removes the loss entries from the outputs dictionary for separate handling. And lastly, a backward pass, which zeroes out any existing gradients in the optimizer to prepare for a fresh computation for gradients. From my evaluation, I would say my algorithm delivers slightly lower accuracy than the original paper, but we are sharing the similar training time on both the 5K and PPR 10K datasets, just as offered by the authors. And finally, the conclusion. Modern image enhancement is not just about achieving the highest quality of visual results. It's about doing so efficiently and adaptively. The development and application of AdaInt within a 3D LUT framework demonstrate a significant stride forward in our ability to perform real-time content-aware image enhancement. This approach reflects a broader trend in computational photography and machine learning, which is the pursuit of algorithms that not only perform well but also adapt seamlessly to diverse content and constraints, pushing the boundaries of what's possible in real-time image processing. Thank you for watching.